Earth's materials, the foundation of understanding geological processes. As we explore Earth's materials, we're going to explore them in terms of three categories. The first are minerals, then rocks, and then we'll touch on soils at the end. So to start with minerals, minerals are the building blocks of rocks. And this is why we are going to start with minerals as opposed to starting with rocks. A mineral has a specific definition. So in order to be considered a geologic mineral, a substance must have the following 5 characteristics. If even one of them is different or missing, it's not considered a geologic mineral. And I emphasize the geologic mineral part because there are minerals, say, in our food and in our soils, but when we're referring to a geologic mineral, it's a specific compound of atoms, and it forms through geologic processes. So the first property that a substance must have to be considered a mineral is that it must be solid. So if you recall, there are 4 states of matter: solid, gas, liquid, and plasma. For matter to be considered a mineral, it must be a solid. And this definition goes on in a little bit more detail about what a solid state of matter is, and that it is solid because the forces are so strong that particles cannot move freely, but they can only vibrate. And so as a result, a solid has a stable, definite shape and a definite volume of space that it takes up. If we have a material or some matter that is in any state other than a solid, it would not be considered a geologic mineral. A geologic mineral must also be naturally occurring. So this material was, made naturally through earth processes. So in essence, the material was not synthetically made in a laboratory. There are synthetic minerals, but we are going to ignore them in this class because we are only interested in a true geologic mineral. The third criteria of matter that would define it as a geologic mineral is that it is inorganic. So the material itself has never been alive, and it contains no organic carbon. It may contain carbon, but not organic carbon. But the material itself may be the product of biological processes. That does not make it organic. It still is inorganic. The fourth property is that this matter must have a chemical composition where that chemical composition falls within a narrow range of one distinct element or compound of 2 or more elements. Essentially, it's predictable and reproducible. There may be some substitutions occasionally at the atomic level for bonding purposes, but effectively the chemical composition is consistent. And lastly, a material would be considered a geologic mineral if it has an internal structure where the ions, atoms, and molecules that compose this mineral are arranged in a predictable repeating pattern that produces crystalline structures. So for example, ice is a geologic mineral. It is solid, it is naturally occurring, it is inorganic, it has a chemical composition of H2O, and an internal structure of that repeating pattern to produce crystalline structures. For example, if you've ever seen a snowflake, it has crystalline structures. or an ice cube. At the molecular level, there are crystalline structures. However, there are other materials like sugar. Sugar is not a geologic mineral because it is the result of organic processes. So it meets 4 out of 5 of these criteria, but because it does not meet 5 out of 5, we cannot consider it a geologic mineral. Now, minerals are grouped into different classes, and these are important when we talk about resources versus crustal rocks. So mineral classes are classified depending on their anion, and an anion is a negative charged molecule. So in this instance, there are 2 mineral classes. The first are silicate minerals, and the second are non-silicate minerals. Silicate minerals have an SiO4 anion, and they are the most abundant minerals in Earth's crust. And so when discussing the formation of new crust, really, those are silicate minerals. Now, sometimes there are non-silicate minerals where there are other geologic minerals that do not contain a silicon and oxygen tetrahedron. And these ones are particularly of importance as we address the resources component of our Earth materials. So non-silicate minerals are any minerals that do not contain the silicon-oxygen tetrahedron anion, though there are many minerals that contain oxygen. And so non-silicate minerals are often of greater economic value, and we use them as resources. They're grouped into different groups called the carbonates, with a CO3 anion, so carbon oxide, carbon and oxygen, and it's usually useful for building materials and manufacturing. Carbonates are really highly used in cement, which releases CO2 into the atmosphere, and they can dissolve with acid. So these are really important when we're talking about carbon sinks and carbon storage and how carbon can cycle in our biogeochemical cycles. There are also sulfates, which is an SO4 anion, so sulfur and oxygen. It's also useful for building materials. Sulfides are another group. They are a host for many of the metallic ores, like lead, copper, and a lot of other ores with high economic value. There are the oxides group, and that's any metal element combined with oxygen. And these are also very economically valuable. There are halide minerals, and that's when a metal combines with a halogen element. And the 2 most common applications are as a highly desirable consumable. So halite is a geologic mineral. It's also known as table salt. And the other is fluorite, and that's commonly used in metallurgy. And the last of the non-silicate groups include native elements. And these are minerals composed of single elements such as carbon in diamond, or gold, silver, and copper. So rocks are actually the amalgamation of one or more minerals or a mineral material like glass. And rocks can be distinguished by 3 rock types. igneous, sedimentary, and metamorphic. And each rock type is distinguished from one another because of the processes associated with that rock formation. So now we're going to cover the 3 types of rocks and how they form. The first is an igneous rock. Igneous rocks form from the cooling and crystallization of magma or lava. And importantly, magma is molten rock beneath Earth's surface, and lava is molten rock on or at Earth's surface. We classify igneous rocks, so we give them names based on their chemical composition or their mineralogical composition and the texture that tells us how these rocks cooled. Was it quick? Was it slow? And things of that nature. There are sedimentary rocks. Sedimentary rocks are formed when sediments undergo a process called lithification. So a little bit of additional information here. Sediments are any loose, unconsolidated mineral or rock particles that have been broken down and or transported by wind, water, ice, or gravity. Typically, sediments are laid down, so to speak, or deposited. That's the geologic term we use. Deposited in thin layers. And when those layers undergo the process of lithification, it results in what we call beds or strata. So lithification is a combined process of compaction and cementation, and it will be the process that transforms sediments into one material, a rock. Sometimes the sediments are very similar. Sometimes sediments are drastically different, and that is a whole other class in itself. But if we use this example here, these sediments are laid down or deposited, and there's overburden. So some sort of pressure, whether that's more sediments laid on top, or maybe there's a tree. Usually it is more and more sediments layering on top of other sediments. But that overburden results in pressure, and that pressure will compact or reduce the amount of space between these sediment grains. And oftentimes those pore spaces, or the spaces between those sediments, are filled with cement, and that cement acts as a glue. And the third type of rock is a metamorphic rock. And metamorphic rocks are formed by the process of metamorphism, where a pre-existing rock undergoes textural and or mineralogical changes from the addition of heat or pressure changes. And what's most important about distinguishing a metamorphic rock from, say, an igneous or sedimentary, the pre-existing rock, which we call a protolith, it must not melt. If it melts, it becomes an igneous rock. And so metamorphism typically results in the recrystallization of pre-existing minerals. They can become larger or more interlocking, or some minerals that are unstable at those temperatures and pressures will break down and new minerals may form instead. But very important to recall that matter cannot be created or destroyed. So if those minerals break down, those elements, they are converted into new minerals, or maybe are flushed out in solution like water in the interim. So those atoms that are in those minerals that are unstable, they don't disappear, they just become part of something new. And as is usually really easy to point out with metamorphic rocks, igneous, sedimentary, and metamorphic rocks can cycle. And they can cycle from, say, an igneous rock to becoming a sedimentary rock, and a sedimentary rock becoming a metamorphic rock. Or a metamorphic rock can be broken down to form a sedimentary rock. And if that sedimentary rock is subjected to enough heat, it can melt and form an igneous rock. There are various avenues associated with these different rock types, and this is known as the rock cycle, because rocks have this interconnectivity. So one rock can ultimately become another rock, and it does not have to follow igneous, sedimentary, metamorphic. A metamorphic rock can become an igneous rock. An igneous rock can become a new igneous rock. And so there are a lot of different ways to cycle between them. And really, as you think about, say, a biogeochemical cycle, rocks undergo their own cycling. It is another way of cycling matter and transferring energy on Earth. And so it's very similar to those biogeochemical cycles we looked at a couple of weeks ago. So now something I want to point out is that there are specific processes that occur on Earth's surface, and when rocks are exposed at the surface, they can undergo what's called weathering. Weathering is the process of changing the physical and or the chemical characteristics of the rock at the surface. So this means the breakdown of rocks and minerals. And soils and sediments are the products of weathering. So when we're discussing weathering, there are two types. The first is mechanical weathering, which is the physical breakdown of rocks. So think like a hammer hitting a rock. That's mechanical weathering. There are organisms that can mechanically weather rocks. There are bees that will drill holes into rocks. That is a mechanical weathering of rocks. There is also chemical weathering, which is the decomposition of rocks from exposure to water and gases. So if you think possibly about limestone, which is a sedimentary rock, it's abundant in the mineral calcite, and calcite is a carbonate mineral. If you recall, carbonate minerals will dissolve with acid. And so groundwater is inherently acidic, and where there are limestone rocks, there often are a lot of caves because groundwater will dissolve these carbonate rocks, and we get a lot of our cave systems. There are biological ways of chemical weathering. There are rocks which in certain environments are covered in lichen, and lichen are this like really interesting fungi algal crust on rocks, and what happens is they secrete an acid, and that acid quite literally eats away at the rock to extract minerals that organism then consumes. And so it's the breakdown of rocks, and sometimes it's consumed, but other times those sediments are deposited in accumulated, and that becomes either sediment to become a sedimentary rock, or it can become soil. And so where there's that accumulation of unconsolidated rock and mineral fragments plus organic matter that's formed at Earth's surface, soil is formed. And what's really important to differentiate between soil and sediment is one, soil is capable of supporting life, and two, sediment is matter that has typically been transported and deposited. Soil is matter that is really close to where it was broken down. It does not travel. So the last thing in our earth materials lecture here are soil horizons. So soils are actually predictable within reason of a series of zones with different colors and compositions. And so this graphic here is showing a sketch version of what we would call a cross-section of soil horizons. The topmost layer, the organic layer, which we abbreviate with an O, is also called humus or humus, depending on who you ask. This is generally where most of that sustainability of life, where life is sustained, here in this organic horizon. Below that organic horizon is the surface A, or the soil horizon A. This is considered top soil humus, but it also has rocks and minerals. Then below soil horizon A is soil horizon B, and soil horizon B is known as the subsoil. It's where the material and minerals are deposited, and between our topsoil and our subsoil, there's this sometimes thin, sometimes thicker layer called the zone of leaching. And the zone of leaching is where dissolved materials percolate down via water. This is also known as horizon E. And so in subsoil B, not only does it have the material and minerals from the pre-existing rocks, but it also has any of that material that was leached from the E horizon deposited in this layer. And the lower of our soil horizons is known as soil horizon C, and that is where the parent rock or the bedrock has been partially weathered or broken down. So if you think about this kind of as a ratio, our soil horizon C, mostly bedrock, our soil horizon A, mostly organic matter, but some rocks, and then our B is really kind of that mix between them. So our bedrock is whatever the crustal rocks are that are being broken down through the processes of weathering. So that wraps up our introduction to earth materials and how they form.